think I'm fine with you. Sorry for the delay. Yeah, I'm there. Okay. Sorry for the delay. The network is not doing very well here. Let me get the rest of the system connected. We'll start. And the first thing we'll do, right off, we'll do word of the day. It goes into the main content. And I have to apologize about I used the word break. So apologize about the last two periods. Did not do a word of the day. All right. So first of all, wrong book. Okay, so we begin by looking at that particular problem. And if you look back at that, and let me see if I can find that. Yep. That was the lecture, but that was not the problem. I'll go back and work today's problem. There it is. I do not know. It must have had a space. Okay. So we worked this last time. What we're going to do now is I'm going to go ahead and go in here and do one other aspect of this. But maybe I'll pick this up off of another problem, because this one has no rotation of that unit. So let's go find another one. And let's see. This one's not so interesting because it has it so that the velocity's going this way and this velocity's going that way, but it's really nice. That's probably not a bad idea. However, this one is more interesting because of the way the velocity has to go along that length, and the velocity has to go along this length. So I'm going to go ahead and solve this one, and then I'm going to introduce this to the next thing, which is instant center. Let me see if there's one that might be more interesting there. That's good enough right now. Okay, so in this one is actually a little easier because you only have to deal with one link here. And on that link, you have the location A and you have the location B. So it doesn't matter which link you want to do. Maybe you want to do that, or you could do this. A relative to B plus velocity of B. Turns out if you stare at this, these are equal in opposite directions. So, one of the things I do know is that, so I'm going to stick with this form of the equation, and I'm going to say the velocity A is equal to, and again, this is a plus omega, that's an x and y, so velocity A is equal to minus 3j. Now, this is omega link AB cross with RB relative to A plus a minus 3j, which comes from right here. So I can list this as I, J, and K. Let me double check the string. Give me a second. Make sure everything is okay. Uh-oh. I'm not hearing any audio. Oh, I hear it. Alright, so since this is in the positive direction, we're going to assume it because I do not know what its value is. Now, I know this is going down and this is going this way, so if you're sitting here, it appears like this link is doing like that, which is actually in the negative direction. But if I assume it in the positive, and then it will come back negative or positive. Now I'm looking for a vector which originates at A and heads off to B. Looks like this. It's 45 degrees, it's 2. So if I were to look at that vector, R, pointing to B, originating from A, is equal to 2 over square root of 2, but it's back this way. So, and if you look at 2 over square root of 2, top times bottom, that gives you 2, square root of 2 over 2. So I believe you get this. So I have a component going to the left, which is negative. I have a component going down, which is negative. And so minus square root of 2 minus square root of 2 and nothing plus minus 3j. And this is the velocity of b. Now I have somewhat run out of space, so I'm going to take the whole problem and shift it to the right. I'm going to come back, increase the pin length because it's annoying that it's, and it also, in fact, I think, well, anyway, so from this, I times, you have this, you eliminate the row, the column, you take that and you write it right there. Minus j times, if you have that, it's a minus here, it eliminates this and this, and you take this as your matrix. And if you're taking the k, there's something on the screen here. You eliminate this, this, and here's your cofactor expansion. So this term gives you 0. This is a positive 0. This is a negative of a negative, or square root of 2 omega AB. Guess what? Same thing here. So what you get is square root of 2 omega AB I minus, the reason you have a minus is this, square root of 2 omega AB J. Now, I did not copy this down. Now, again, let's stop for a moment. Let's recognize this is its own entity. In fact, let's stare at it. Let's say, okay, I have a vector which is, let's identify what this whole term is. It is the velocity of B as observed as if you were sitting on A. Let's take a look at this. Assuming that, give me a second here. Okay, take that. If, in fact, you were situated such that this was the case, and recognizing this is positive, so I have assumed this to be positive, so I would get a velocity in which it would be positive amount in the x and a negative amount in the y direction. This is, in fact, what I get right here. Next, using our technique of recognizing that A cross B, giving a vector of C, any A vector, any V vector would give some vector C. In fact, that would be 90 degrees to A and 90 degrees to B. So in fact, because of the way the cross product is, it's perpendicular to A, and C is perpendicular to B. Therefore, A dotted with C gives you 0, and B dotted with C, which is the same as C dotted with B, gives you 0 as well. What this means, if you look back up in the equation, A happens to be negative AB, B, so now back here, happens to be RBA, and this happens to be the velocity of B relative to A. Therefore, this blue vector is perpendicular to this one and also perpendicular to that one. The first vector is useless in that if you dot a vector that looks like this against this, by nature you'll always get a 0. There's no information that you can get out of that one. But if you take this vector and dot it against that vector, what do you get? Take the first times this, gives you minus square root of 2 times square root of 2 comes from negative AB plus, and when I take this one and multiply times that, to be minus square root of 2 times a minus square root of 2 negative AB. If you look, this is positive, this is negative, values are the same. In fact, it's a check. And it turns out that is correct. So we move on from there, and basically recognize something interesting here, and that is, I don't know omega, I don't know velocity of B, but I know it's sitting in this track. So you're going to have to either assume it's going this way, or you're going to have to assume it's going that way in that track. It doesn't matter which way you decide. I really, this is one of those cases in which it's so close, I can't tell you, but I will tell you that I have 30 degrees here. So if I have a vector going in this direction, and I'm just going to assume it that way, if it comes up negative, it switches. So I'll say capital V, B, and the velocity of B will be the component this direction minus the magnitude of velocity times the cosine of 30 I plus, because there's a component going up, velocity of B sine of 30 J. Now that I've done that, I'm going to do this. Copy it. And move to my back here. I'm going to paste that. The next thing I'm going to do, I'm going to make use of a pen. And then I'm going to copy this. Get a copy, and I'm going to put it about right there, and it's kind of the wrong place. And this is the equation I get. Now, this tree, this is the case, and but this equals this, so I really don't need any of that. But I'll leave it there for the time being. So what I'm going to identify is the I components, and then I'm going to identify the J components. And then I'm going to come down here and say, hey, I'm going to split these into the I components, and then I'm going to grab the green, easy cosine 30. Now, technically, there's supposed to be equal sign right here. Equals to the green over here, which is square root of 2. We'll get AB for the J component. I get the blue, and the blue here. Equals to minus square root of 2 AB minus 3. So now I'm sort of stuck. And the way I'm stuck is I've got to move something to the other side. So what I'm going to do, I'm going to have it equal here. The minus, move this to the other side, so it becomes a plus. If it moved over and that one did not, look at that. So now I can make a matrix out of it. And what I can do is cosine 30 minus square root of 2. And of course, this is this column. Coefficient for this, and then the coefficient for this. Now, should be able to put this in octave. Call the first matrix K. There's your matrix on the right hand side. The inverse K multiplied times the right hand side, and you get the velocity C, and it's 2.1962. And there's AB, 3.2, 1.34, 49. Now, this is telling me that instead of the velocity going this direction, it's actually going this direction. That makes me feel a little uneasy. But I'm going to go in here and check the answer of the back of the book, which is Feb-16-2022. Is that 16-12 or 15-12? 16-12. Oh, this is P. This is a P. I'm not sure if F says before or after. Maybe this is 12, 9, 10, 11. That's 11. Okay, here's 12. Okay, so it looks like I got the wrong answer, I believe. So, let's see if we can diagnose what happened here. There's part of me that kind of felt like, okay, and what I'm going to do, instead of just coming up with this off of here, I'm going to use this opportunity to double check using a different method. Okay, so here we go. Let's see if I can plug here. Maybe I can select it with the mouse. Hang on. I'm going to copy this, and I'm going to introduce this to something else to double check. I don't think I got the right answer. So what I'm going to do is, instead of working my way off of it, first of all, I doubt the angles and everything. So here's what I'm going to do. I'm going to try my best to redraw this thing. Okay. So it is a distance of 2. Okay, so what do I want 2 to look like? I don't know. Let's see. Let's see. That would 2. That's going to be too short. I'll say this is 2. So halfway. Do that. So this is 1. So those be 2, 2, 3 takes. 1, 2 takes. So here would be 2. I am not able to. Here's 2. Is that correct? No. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Here's 2. Now I'm going to tilt this up at 30 degrees. And at 30 degrees, I'm trying to get this to line up here. There. So this is the direction of the velocity. I'm going to assume it's going this way. Okay. So the other thing is the velocity from this end is going down. So let's introduce ourselves to instant center in order to check this. In an instant center, here's what an instant center is. Hang on. Okay. In an instant center, let's assume you had an object, and this object happened to be connected to a rod out here and was spinning about this. And I had 2 points on it, and these 2 points will go in this speed and this speed. Now, if I'm looking and I have the velocity direction of 2 locations, how can I actually go back and determine that's where it appears like it's rotating about? Here's what you do. Constructed this under the assumption that it was rotating about this point. What does that mean? That means this is 90 degrees. So, if an object is rotating about a point, draw a line that is 90 degrees off the direction of the velocity, and you simply draw that line. If you have another point, and it so happens to have its direction, you can draw another line off of it. Where they cross is at what's commonly called the instant center, meaning it appears like it's rotating at that point. So again, you have two objects. I'm just going to leave that there. I'm going to try to move over here. You have an object. So you had a velocity that was going this way. And then over here, you had a velocity that was going that way. And you're like, where does it appear like it's rotating about? Take a 90-degree line and just draw it. So take another 90-degree line and just draw it. This is where it appears to be rotating about. Again, let's do it again. You have a rod here. This velocity is going this way, this velocity is going that way. What do? You draw a 90 degree to it. You draw a 90 degree to it there. It appears as though this rod is rotating about here. Now let's compare this with this, and suddenly we actually might be able to make some sense of this. Okay, I tried to make, I don't know what this means. Okay. I tried my best to make it look like we were to scale here. Now, to know that goes straight down, so in light of this being a different, I just draw a line. This line is 90 degrees today. Now this one was kicked up at 30. So what I need to do kick that one to 60. Okay. Appears as if this rod is rotating back. Now, in an XY sort of sense, this is a positive rotation, which indicates that that's positive. Let's make it like that instead of X. That's a positive rotation. Appears like to me that's a negative rotation. Did we get a negative rotation? Yeah. Now, what we're going to do here is kind of interesting. So, using the concept that this is of distance 2, and if I did a reasonable job, let's see. Yeah, I didn't do a good job here. So this distance right here so this is a distance 2. And it looked like, okay, I'm going to count this as number of ticks. Okay, so I got 1, 2, 3, 4, 5 in each one of these. 5, 10, 15, 20. 25, 30, 35, 40, 45, 50, 55, 60. So there are about 61 ticks here equals 2 meters. So I'm scaling my drawing here. 61 ticks is equal to 2 meters. So now, how many ticks you have on a dog. Let's look at the distance between here. Now, ticks are the number of points. So 1, 2, 3, 4, 5, 10, 15, 16, 17, 18. Looks like to me about 18 ticks here. Let's see how many ticks are down here. Okay. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. It's like 50 ticks. 50 ticks from here to here. Now that's a distance. I don't have to necessarily move it 2 meters. So if this is a new distance, say number of ticks, so 61 ticks is equal to 2 meters, then a tick is a unit of measurement. Now watch this. Here's the velocity. I know it's equal to 3. I think it's equal to 3. Yes, it's equal to 3. But it is also equal to omega r. Now, if I want to convert 18 ticks to meters, and I'll go ahead and do it just because I'm going to be stuck here with meters, and this will be radians per second, and this is meters per second. So 2 meters is equal to 61 ticks. And if I multiply that times the distance, say B1 over 18 ticks, and I get a distance D1 equal to here. So 2 times 18, that is 51, gives me 0.59 meters. So this is distance 1, 0.59. What does 50 ticks give you? Okay, so 2 meters is 61 ticks times distance 2, we'll call this distance 2, over how many ticks? 50 ticks. Tells me that distance 2 would be 61 times 50 gets me about 1.6393. If I saw that correctly. Now, this is number of meters. So now, what is this? Omega times D1.59 gets me an omega of 3 divided by 0.59, or, and this is approximate because I'm just 5.08. So my omega is about 5.08. Look back at the solution here, and you can see pretty close. Now let's go over here and notice if I have this thing, and it does appear to be going at 5, and I'll stick to mine. I know he said 5.02. Then I had this, and then multiply this. So if I want to know this velocity, it's equal to the omega times distance 2. Now this r here is this distance. So 5.08, I'm going to stick to 9. And my distance is 1.6393. And essentially, I get okay, so take that, multiply it times 1.6393, 8.33, 8.335 So just like that. Now, here's the funny thing. This was rule of thumb. I mean, I was just using this ruler here, and I got pretty close. Now, it's getting close to the end of time. What I'll do next time is I'll make this more official in that I'll use trig in order to find the exact distances of all these. So if this were 2, and I have an angle here and an angle here, they'll use law of cosines to find this d1 and d2, and we'll refine in and get these straight on. Still haven't accessed or figured out what I did wrong here, but we'll do that after we use the other technique to get the right answer. So I'm going to call it quits, and we'll come back here next time.